Universal set and other sets introduction. So let's move on to understanding how the universal set interacts with other sets. In the sections we've covered so far, we've already laid the groundwork by defining what a universal set is. Now, we're going to build on that foundation and see how it relates to other sets we might be working with in a particular problem. The really important thing to grasp here is this. Within any given mathematical discussion or problem, all the sets we're considering are actually inside the universal set. Think of it like a big box, and all our other sets are smaller boxes fitting neatly inside. Because they are contained within the universal set, this automatically means that all these other sets are what we call subsets of the universal set. We'll be using that term, subset, a lot, so it's important you get comfortable with it. We're going to break down this concept step by step, with examples to make sure it's crystal clear. We'll be diving deeper into what a subset actually is on the next slide, but for now, just remember this core relationship. The universal set is the overarching set, and everything else we talk about lives within it. Understanding subsets. This slide formally defines what it means for one set to be inside another, which we call being a subset. It states that a set, which we're calling A, is a subset of a set U, and we write that as A is a subset of U, if every single element that's in set A is also found within set U. The slide then gives a simpler way to say the same thing. In simpler terms, everything that's in set A is also in set U. So let's move on to understanding what a subset is. As we discussed on the previous slide, we have this idea of a universal set, a big set that contains everything we're interested in for a particular problem. Now, within that universal set, we can have other sets. Think of it like this. If you were to list out all the things in set A, each one of those things must also be on the list of things in set U. It's a really important concept, and we'll be using it a lot as we move forward, especially when we start looking at set operations like unions and intersections, which we'll cover in later slides. So, make sure you have a good grasp of this definition. We'll solidify this with some examples on the next few slides. The universal set as the containing set. So let's move on to slide 3. This slide really solidifies the idea of what the universal set is and how it relates to all the other sets we'll be working with. Now, the second point says, any other set we define within that context will necessarily be a subset of U. Think of it this way. When we start a problem involving sets, we first define what our world is. That world is the universal set. The letter U is just a standard notation mathematicians use to represent it. It's the biggest set we're considering for this specific problem, and it holds everything we're interested in. Everything else we talk about will fit inside this set. Remember from the previous slide that a subset is a set where every single element is also found within another, larger set. Because the universal set contains everything relevant to our problem, any smaller set we create, like the set of even numbers or warm colors, as we saw in the examples, will automatically be a subset of U. It has to be, because that's how we've defined our universal set. This is a crucial concept, so make sure you understand it. We'll be building on this idea as we move forward, especially when we start looking at set operations like unions and intersections. And as we'll see on the next slide, even very simple sets like those with just one element or even empty sets fit into this framework. Example 1, even numbers and divisibility. Let's move on to our first example to really solidify this idea of universal sets and subsets. Here, we're going to define our universal set, which we'll denote with a capital U. We're saying that for this particular example, our universal set U consists of all even numbers from 2 up to 10. So, U is equal to the set containing 2, 4, 6, 8, and 10. Remember, the universal set contains everything we're interested in discussing within this problem. Now, let's define another set, which we'll call A set. A will contain numbers that are divisible by 4. So, A is equal to the set containing 4 and 8. Now, this is the crucial part where we check if A is a subset of U. Look closely. is every single element that's in set A also found in set U? Let's see. We have 4 in A, and 4 is also in U. We have 8 in A, and 8 is also in U. Since every element of A is also an element of U, we can confidently say that A is a subset of U. We write this mathematically. As A is a subset of U, the symbol for subset looks like a small contained within a larger set, and we read it as A is a subset of U. This example demonstrates the core principle. If everything inside one set is also inside another, then the first set is a subset of the second. We'll build on this with more examples, and then we'll look at some special cases like empty sets and singleton sets, so keep this example in mind as we progress. Example 2, primary colors. Let's move on to another example to solidify our understanding of universal sets and subsets. Now, on this slide, we're going to consider colors. Let's define our universal set, which we'll denote as U, to be the set of all primary colors. So, U equals the set containing red, blue, and yellow. Remember, the universal set contains everything we're interested in discussing within this particular problem. Next, we define another set, which we'll call A. Let's say A represents the set of warm colors, and in this case, the warm colors we're considering are red and yellow. So, A equals the set containing red and yellow. Now let's check if A is a subset of U. Remember, for A to be a subset of U, every single element that's in A must also be in U. If you look closely, red is in both A and U, and yellow is also in both A and U. Therefore, every element in A is also found within U. This confirms that A is indeed a subset of U, and we write this mathematically as A is a subset of U. So, A is contained entirely within our universal set, U, just like we discussed in the previous slides. Keep this in mind as we move forward, because understanding subsets is crucial for more complex set operations we'll explore later, like unions and intersections. And remember, even sets with just one element, or even the empty set, can be subsets of our universal set, as we'll see shortly. Empty sets and singletons. So far we've been looking at how sets can be contained within our universal set, how they act as subsets. Now, let's consider some special types of sets. This slide introduces two of them, the empty set and the singleton set. First, we have the empty set. It's denoted by a symbol that looks like this, a slightly curved, almost circular symbol. We call it the empty set symbol, or sometimes just phi. It can also be represented by a simple pair of curly braces with nothing inside. The key thing about the empty set is that it contains no elements. Now, this might seem a bit strange, but it has a very important property. It's a subset of every set, and that includes our universal set. Think about it this way. If a set has absolutely nothing in it, there's no way it can have an element that isn't in another set, right? Since there are no elements to check, it automatically satisfies the condition of being a subset. It's a bit of a logical trick, but it's fundamental to set theory. Next, we have the singleton set. This is simply a set that contains only one element. For example, a set containing just the color green, we'd write that as green inside curly braces. Now, whether or not a singleton set is a subset of the universal set depends on whether that single element is also an element of the universal set. If the element is present in the universal set, then yes, the singleton set is a subset. If it isn't, then it's not. We'll see this illustrated with more examples on the next slide, but it's important to remember this condition. Just having one element isn't enough to guarantee it's a subset. That element must also be within the boundaries of our universal set. Example subsets with universal set. Let's look at this slide. We're going to solidify our understanding of subsets and the universal set with a few more examples. Here, we're defining a universal set, which we're calling U, and it contains 3 fruits, apple, banana, and orange. So, U equals the set containing apple, banana, and orange. Remember, the universal set holds everything we're considering in this particular problem. Now, the first statement says that the empty set is a subset of U. We write this as empty set is a subset of U. Remember, the empty set is just a set with absolutely nothing in it. And we've already discussed that the empty set is a subset of every set, including our universal set U. Simply because there's nothing in it that isn't also in U, it's a bit of a quirky rule, but it's important to remember. Next, we define a set A, which contains only the element apple. So, A equals the set containing apple. Because apple is an element of our universal set U, we can say that it is a subset of U. We write this as A is a subset of U. This perfectly illustrates the definition. Every element in A is also found within U. Finally, let's look at set B. We define B as containing only the element grape. So, B equals the set containing grape. Now, if we look at our universal set U, do we see grape listed? No, we don't. Therefore, B is not a subset of U. We show this by writing B is not a subset of U. This is crucial. For a set to be a subset of the universal set, all of its elements must also be in the universal set. This slide is a good check for your understanding. It reinforces that the universal set is the overarching set, and any set containing elements not found in the universal set cannot be a subset. In the next slide, we'll visualize this relationship to help it stick even more. Visualizing the relationship. Let's move on to visualizing this concept of universal sets and subsets. This slide uses a helpful analogy to make it really clear. Imagine a large container. Think of a big box or even a warehouse. This large container represents our universal set, which we denote as U. Remember from the previous slides, the universal set contains everything we're interested in discussing within a particular problem. Now, all the other sets we define, like the set A, containing numbers divisible by 4, or the set of warm colors, these are like smaller containers inside that large container. So, picture smaller boxes placed neatly within the bigger box. Every item inside those smaller boxes must also be inside the big box, because those smaller sets are subsets of the universal set. That means every element within those smaller sets is also an element of the universal set. Finally, the empty set, which we represent as a symbol that looks like a curly brace enclosing nothing, is like an empty box inside the large container. It's a box that has absolutely nothing in it. And because it's empty, it automatically fits inside any container, including our universal set. This is because there's nothing in the empty set that could possibly be outside of the universal set. This visual should help you understand how all these sets relate to each other. We'll build on this understanding as we move forward to more complex set operations, so make sure you have a good grasp of this idea. We'll be summarizing all of this on the next slide and also pointing out some common mistakes to avoid. Key takeaways. Let's recap the key ideas we've covered regarding universal sets and subsets. This slide, titled Key Takeaways, summarizes the most important points for you to remember. Firstly, it states that the universal set contains all elements under consideration in a given context. Remember, we define the universal set, denoted by U, at the beginning of a problem to clearly define everything we're working with. Everything else we discuss will fall within that set. Next, it reinforces that all other sets defined within that context are subsets of the universal set. A subset, as we learned, means every single element found in that smaller set is also found in the larger universal set. We represent a subset relationship with this symbol, is contained in, and read it as is a subset of. Now, this is a crucial point. The empty set is a subset of every set, including the universal set. The empty set, which we denote with either a symbol that looks like a curly brace closing, or simply as a set with nothing inside, contains absolutely no elements. Because it has no elements to not be in the universal set, it automatically qualifies as a subset. It might seem a little strange at first, but it's a fundamental rule. Finally, singleton sets, those sets containing only one element, are subsets of the universal set only if that single element is also an element of the universal set. If the single element isn't in the universal set, then the singleton set is not a subset. Keep these 4 points in mind as we move forward, because they'll be essential for understanding more complex set operations like unions, intersections, and complements, which we'll explore in the next section. And remember, Always double-check your work to ensure you haven't accidentally included elements outside of your defined universal set, as we discussed on the previous slide about common mistakes. Common mistakes. Alright, so a really frequent error students make, and it's easy to do, is defining a set that includes elements that aren't part of our universal set. Remember, the whole point of the universal set, which we denote as U, is that it contains everything we're currently talking about in a particular problem. If you introduce something outside of U, you're breaking that fundamental rule. It's like trying to fit something into a box that's simply too big for the box. It doesn't belong in that context anymore. So, what I want you to always do is double-check. Before you declare that one set is a subset of another, meticulously verify that every single element within that smaller set is also present within the universal set. This is the core of the subset relationship. Finally, don't forget about the empty set. We talked about it earlier, but it's a surprisingly common source of errors. The empty set, which we write as a symbol that looks like an empty bracket, is a subset of every single set, including our universal set. This might seem strange at first, but remember why. The empty set contains no elements at all. Therefore, there's no way it can contain anything that isn't in the universal set. Forgetting this can lead to incorrect conclusions when you start performing operations with sets, like unions or intersections, which we'll cover in future lessons. Let's move on to the final slide, where we discuss some common pitfalls to avoid when working with universal sets and subsets. So, keep these common mistakes in mind, and you'll be well on your way to mastering the concept of universal sets and subsets.